let's see. We'll start with what your paper should have looked like. You probably marked an X down here to indicate that that was directly below where the ball was launched. And then you had a bunch of spots out there representing where the ball struck the ground when there was no collision. And then you had a bunch of spots over here and a bunch of spots over here representing where the ball struck the ground due to a collision. Sound familiar? So I told you to go ahead and circle all those and then draw a line from the launch to here. This represents V0. Then draw a circle around those, and draw a line to the middle of that, and draw a circle around those, and draw a line to the middle of that. This represents what happened when there was a collision, and this is the velocity for the ball that went to the left and the velocity for the ball that went to the right. Does this look like what you guys did? It's bad enough I have to overhear Grog over there. Who's tapping? All right, so you don't actually have velocities. I'm saying these represent the velocity. But you have the height of the table, so you could calculate how long it took those things to reach the ground, and from there calculate the velocities. I think a reasonable argument could be made that you don't need to calculate the velocities and that you could just use the distances. I think a reasonable argument could be made for that. And if you were to make such an argument in your lab, you wouldn't have to calculate all the velocities. You could just leave it in terms of the distances. I think a reasonable argument could be made for that. Follow me? You have to make the argument. Next, I said to you, I wanted you to demonstrate conservation of momentum. So conservation of momentum would state that m v naught would have to be equal to m vl plus m vr. But this is a vector statement. And because it's a vector statement, you can't just do that, because you have to compare them vectorially. The only way you can do that with your math is to break it up into two one-dimensional problems, an x-dimensional problem and a y-dimensional problem. So, set the direction of the original ball as perhaps the y direction and the other direction as the x direction. And then take and break these up into their components. That ball has a x component and a y component. This would be VRY. This would be VR. Nope, that would be VRX. This would be VRY. And let's see. This would be the components for the next one. This would be VLX. This would be VLY. You've got the angles. You can break them up into their components. This allows you to say, all right, in the x direction there was zero momentum, and afterwards there was mVLX plus mVRX. In the y direction, there should be mV0 equals mVLY plus mVRY. Now, seems to me as long as the balls were the same mass, you don't need the mass of the ball either to demonstrate this. It seems like that would cancel out over here, and it would cancel out certainly here as well. The real thing, though, is that you're unlikely to show that these are equal for a number of reasons. One of them is you have a group of targets. You don't actually know which one of these goes with which one of these, do you? You just have range. In fact, the whole idea is to have done this repeated times so that you can get a group and you can show that your results work for more than just one example. The problem is that they're not going to be perfect, right? Due to the fact that there is some amount of variance in the values. You need to include that. You need to see if you are equal within the range of error. To do that, and this is why you took a picture of these, you need to figure out what the range of error is. How much plus or minus is there in the x direction? And how much plus or minus is there in the y direction? You should find the plus or minus for the x direction and the plus or minus for the y direction. If your data shows groups that are all approximately the same, you could probably use the same plus or minus for all the values by just measuring one of them. But if you have like groups that are weird, like they are oblong or something like that, then you might have to do something else. Hopefully your groups are nice and relatively fit a relative histogram of possible landing sites. So basically you're just measuring the diameter in the x direction and y direction and cutting it in half and making that your plus or minus. Does everybody understand what I'm asking you to do? So you could say VLX plus or minus the error, is it equal to minus VRY plus or minus the error? Now you could ask that question. If it is within the error, you've shown that the momentum was conserved in the x direction. And you could do something similar in the y direction. Is V naught plus or minus the error equal to VLY plus or minus the error plus VRY plus or minus the error? Pretty straightforward? Now, here's the crux. Here's something I want you to kind of hear me out about. I don't know if you're going to prove it or not. In some cases, your collisions may not have conserved momentum for a number of reasons. There could have been an external force on the system that slanted your results. You could have not done a good job marking where this was. That would slant your results as well. There are a lot of things that could have happened that will make your results maybe not work out like you'd like them to. Your job is twofold. First, you just explain your results. I was or was not able to show conservation of momentum. I want that. I want to look for that sentence in there. Next, perhaps offer an explanation as to why you couldn't show it if yours doesn't show it. Something reasonable. You're going to do this 3 times, right? 1 for each set of data. If you weren't here on Friday, I will let you use 2 data sets from your group, but you will have to take 1 data set on your own. You can either come in and work with other members who are going to be doing this tomorrow morning, and if you do, you'll have to be super quiet because I'll have a meeting in here, but there will be a ramp set up over by where those fans are and where the computer card is, and you can go in there and just take the data. All right? Any questions? What I'm expecting? I give you a week on labs. I'll give you a week. So next Tuesday. Okay. All right. I want to teach you one more thing. You are all super familiar with translational motion. Translational motion, again, talks about something changing location. So if we look at the translational motion variables, these are our translational motion variables, right? We know that they have a calculus relationship. That's still true today. There's a calculus relationship between these variables. meaning the velocity is the rate of change of position, and the acceleration is the rate of change of velocity. That relationship exists, but we also know that for an object experiencing a uniform acceleration, we have a group of motion equations that we can employ. Rotational motion is not going to be any different. We already know about some of this because of uniform circular motion. So we know things like we can use omega naught and omega. Right? We use that first semester to describe things in circular motion, the rotational speed. Remember that first semester? Well, we're just going to add a few more things now. So these stand for angular or rotational velocity. Initial and final. And they are vectors. We just described how to deal with the vector. But instead of having a change in position, we will have a change in the direction you point. Right? Change in orientation, the direction you face, delta theta. So I could turn 2 radians counterclockwise. Right? That's what we would say. That's delta theta. Now, this one's new for you, but we're going to use a lowercase alpha for angular acceleration. If an angular velocity can change, then there's an angular acceleration. And of course, time is just time. Now, it shouldn't surprise you, but omega is the rate of change of theta, and alpha is the rate of change of velocity. That shouldn't surprise you. That's still going to be true. Everything's the same, just with the word angular or rotational in front of it. On the other hand, all of these can be in radians or degrees or rotations or revolutions. Those words should be familiar to you, and you should have some knowledge of the unit conversions. That one rotation is 1 revolution, and they equal 2 pi radians, and they equal 360 degrees. Right, you should know that. I'm assuming you do. We don't use degrees very much in this. And somebody asked, if we're going to be using radians so much, do we have to change our calculator to radians? No. You only change your calculator to radians or degrees if you're using sine, cosine, or tangent. That's the only part in your calculator where that matters. The rest of these are just numbers. On the other hand, since these things are true, it shouldn't be a surprise that if we have a relationship based on constant acceleration, that there will likely be an angular relationship based on constant angular acceleration. Can you translate the rest of them? I found in 3rd and 6th period that they couldn't, and I was sad. But you just replace anything with a delta x with a delta theta, anything with a v with an omega, anything with an a with an alpha. So, because I can't trust, I would love for that to be true. I don't even know if what you have written down on your note card is accurate. I know it's what you're looking at, Viv.
Yeah, this is accurate.
We hope. Bruh. Look good? Familiar? Now, you get 3 of these on your equation sheet, pretty sure. But this isn't all we've talked about. If you remember, we've talked about more. Once we have things that are moving, that are spinning, we should not forget that for spinning things, there is the possibility that we might be tasked with dealing with centripetal motion. Right? Things that spin could have objects on them that have to stay attached, so they have to have a certain centripetal acceleration. That's going to come up. But also, things that spin can have a linear component to motion too. So if you'll think back to first semester, if you're on a merry-go-round and you and your friends each choose horses on the merry-go-round, the merry-go-round can have a single angular speed, but you three each have different linear speeds, right? Your linear speed or your tangential speed is related to how far away you are from the axis of rotation. Does that sound familiar to you guys? I'm hoping. Here, let's do a quick example. We have 5 minutes left. You stand on the ground, but 3 of your friends each get on 1 horse each, and all the horses are 1 meter apart. So this is 1 meter, this distance is 2 meters, and this distance is 3 meters. Ready for the problem? The merry-go-round starts from rest, and in 10 seconds gets up to its operating speed. When it's at its operating speed, you standing on the floor see your friends pass you once every 4 seconds. What was the angular displacement of the ride getting up to speed? And what was the angular acceleration of the ride? Does this sound like a motion equation problem to you guys? Let's talk about the information that I gave you. Can you name one piece of information that I gave you? Go ahead. What's that? Started from rest. Excellent. What's another piece of information I gave you? Yep. Takes 4 seconds for a rotation. Where would I put that? So it got up to speed, and when it was up to speed, my friends passed me once every 4 seconds. So that meant the ride must be making 1 rotation every 4 seconds. What else did I give you? How long does it take to get up to speed? 10 seconds. You guys see all that? It's all the same things we've done before. But generally, sometimes it's a little harder because the angular velocity one can be told to you so many different ways. When first semester, something was either so-and-so meters per second or such and such, centimeters per second. Here we have a wider variety of ways it can be presented. But once I have this, I didn't specify what the units had to be for the answers. Just pick a relationship and solve for what's missing. For example, I need angular acceleration. There's got to be a relationship that has these 4 things in it, right? So I'm thinking omega equals alpha t plus omega naught, or 1/4 equals alpha times 10 plus 0, so alpha is 1/40 rotations per second squared. Easy enough? Still need to figure out delta theta. Gonna need a relationship that can do that. Bound to be one. You know me, I always suggest you guys use as much given information as possible. So based on what's there and not wanting to use alpha, I'd probably use delta theta equals 1/2 omega plus omega naught times t. That good for you guys? So delta theta equals 1/2 times 1/4 plus 0 times 10. Not terrible. Of course, this gives you 5/4 rotations. The whole thing was in rotations. All right, we've done our first angular kinematics problem. Now that the ride is up to speed, what's the linear speed of your friends? Do you guys remember how to do that from first semester? There's a way to do it using circumference, but I gave you another way. Do you remember what it was? The tangential value, the tangential velocity, equals the angular velocity times the radius. I gave that to you first semester. But now we're going to expand it, because it works for all of them. Delta x equals delta theta times r. Tangential acceleration equals alpha times r. However, these have to be in radians for this to work. They have to be in radians for this to work. So if you don't remember how to convert to radians, you will have to remind yourself. I suggested unit multipliers, and I still would encourage you to consider using unit multipliers in doing your conversions.